Hey guys, so this is the last video of section 1, and we are going to be talking about another experiment in quantum mechanics. Now this may be, the quantized energy, yeah, that's one thing. This may be the most disturbing experiment thus far in quantum mechanics, right? It is very disturbing, it's very unsettling, and it will eventually, as we will see soon, cause us to completely have to abandon our idea of reality. We're going to have to really start with a brand new framework of physics, and that's what we're going to be doing in the next section. So this experiment really is going to bring us all of the quantum phenomena that we are going to be discussing. So this is a really big experiment. It's called the Stern-Gerlach Experiment. Stern, named after the scientist who performed it. Stern-Gerlach Experiment. Okay, so the first thing these guys figured out, right, is electrons have these two weird properties. They didn't know what the properties are. We now know what they are. It's called spin, right? But how I saw it presented in a course from MIT, and I'll have that link in the description. It is a beautiful presentation of this. So I'm actually going to do it how Professor Alan Adams from MIT introduced this in his introductory quantum mechanics course. And what it is they found these two properties of electrons, right? Electrons have this property, it's called color, some property called hardness, right? And with its color, the color can either be black or white. And the hardness can either be hard or soft. Right? Now, this is a little bit interesting, right? A binary property of an electron. That's a little bit weird, right? It's almost as though the electron's like a coin. It's either heads or tails, right? And what they did, right, is they shot an electron basically into a box with the magnetic field. Into a box, and the electron came out in either one of two trajectories. No matter, they ran this experiment over and over again. It would only come out in one of these two trajectories. Never a third trajectory. Always one of these two. And so this was a little bit weird. They really couldn't explain this result, right? And we're going to call those two trajectories. One of them is one of them is being black and one of them is being white. And they found that if you set up the box a different way, you also had two trajectories. And that other box, right, we'll call hardness, and it will measure either if the electron is hard or if the electron is soft. Now, how do we measure these properties? Well, we have a box, right? And so I'll have a color box and a hardness box. And if you send an electron into the color box, it will either come out as white or it will come out as black. And if you send an electron, these are electrons, into a hardness box, it will either come out as soft or it will come out as hard. That's an H, right? So, the first disclaimer I need to make before we go any further in this is there's nothing about these boxes that are making the experiment go this way. The boxes aren't defective, right? You can do this experiment in any way. There's a ton of different ways that you could separate out these electrons into hard or soft. We know mathematically the way, right, the way we're doing it, it's perfect. There's no better way to do it. There's no theoretically better way to do it, right? And that's one important thing that we're going to have to deal with. That the results for this experiment aren't because of an error in the experiment. It's because of the nature of reality. And you'll have to take me on that. And there's ways to show that, right? And we'll develop those throughout this course. All right. So hopefully you had that down. Now let's go and see what different things we can do with this experiment to get us some really interesting results. So first, let us just take a color box. We're going to send a bunch of electrons through it, right? This is not one electron, but it's an electron beam, right? Well, it'll either come out black or white. And we know, in fact, from this experiment, that the electrons here will come out 50% is black, or actually, for consistency, I'll have 50% white up here, 50% black here, right? We also know, right, that if we send an electron into a hardness box, right, it's the same thing. 50% will be soft, 50% will be hard. Okay, so now what we're going to do, I'm going to erase this bottom part, is we're going to block off all of the black electrons, right? Sorry, not to do this. We'll block off these black electrons, right? We're going to have some blocker so that it catches the electrons. They're not allowed to go anywhere. Okay? And we're now going to put up another color box, right? Which will take these electrons. Right? Now these electrons should all be white, right? And so now what happens? Well, in fact, if you measure the electron as white, if you measure its color again, they're all going to be white, right? If you put white electrons in, the color box will read them all as white. So this property isn't just going to be oscillating, right? If we measure them as white, we measure them again, they'll be white. 100% of these will be white, and 0% will be black. Right? Now we can do this also if we blocked off all the white electrons, put all the black electrons into a color box, 100% would come out black, 0% would come out white. Right? Same thing with a hardness box. If we sent the electrons into a hardness box and we picked all the hard ones out and put them into a hardness box, all the electrons would come out hard. If we took the soft ones and put them into a hardness box, they'd all come out soft. So this is interesting, okay? We can deal with this. Now, this is our extremely unsettling part. Now make sure you had that written down. If you don't, rewind. So, this part of our experiment is extremely, extremely unsettling. I've got my color box. I send in electrons, right? 50% come out black, 50% come out white. So I put it now into a hardness box, right? Well, I put all the white electrons into a hardness box. It turns out that %50 will come out hard. And remember, I'm putting it this way so that you can kind of see the black electrons don't go into the hardness box. It's just the white electrons. 50% will come out hard, 50% will come out soft. Right? So we've got 50% black, 50% white. The white electrons go into a hardness box, 50% hard, 50% soft. Now, it will work the other way. Remember, color and hardness, right? They act the same way. So if we put a hardness box first and a color box second, we'd still get the same 50-50 distribution no matter if we, send in white electrons, black electrons, hard electrons, soft electrons. You can switch up color and hardness. You can switch off black and white, or we can switch up hard and soft. The results will be the same. All right, so I'm just going to show it one way. We'll start with the color box, then the hardness box. But it will work if we start with the hardness box and then do the color box. Okay, now, this isn't too unsettling, right? But if I put us into a color box now, right? Well, remember, if we measured color and then measured color again, it stayed the same, right? So now I measured color. I've got all my white electrons here. Now I've got the soft electrons, so these electrons should be white and soft, right? Well, let's see. We would think, and we would hope, right, that it will come out, well, they'll all be white, right? Now, if we measured hardness again, they will all be soft, right? But now if we measure color again, it turns out 50% will be white. And 50% will be black. But wait, we already measured these electrons to be white. Well, apparently, measuring the hardness affects the measurement of the color. This is a pure fact of reality. There's no way we can set up this experiment so that this does not happen, right? It's not just the operations of the hardness box that somehow mess up with the color. No matter how we measure the color, it will always, any measurement of the color or any measure of the hardness, right, will affect the measurement of the color, and vice versa. Same measurement of the color, right? If we put them into another hardness box, took all the white ones, right? These are not soft and white electrons. They're all white, right? And a hardness box will bring it back 50-50, right? And so this is a little concerning, right? And now, one more concerning fact. I'm going to repeat this procedure. Send an electron in, or electron beam in. This is color. I got 50% white, 50% black. Put it into a hardness box. I'm going to get, again, 50% hard, 50% soft. Right? But now what I'm going to do is, right, I've measured the hardness. Now I'm going to combine these beams, right? So I'm going to I'll have some mirrors. The mirrors won't affect anything about the hardness or color or anything. They'll be perfect mirrors and they won't affect anything, right? Well, I'm combining these beams again. So I've measured the hardness, right? But now I've combined the hard and soft electrons. I'll put them into another color box, right? Now, naturally, if I put it into a hardness box, right, it will come out 50-50. If I put it into a color box, right? Well, we did measure the hardness, so maybe we'll get 50-50 again, right? But no. In fact, if we measure the hardness but then recombine the beams, 100% white, and none will be black. Right? So combining the beams will still do this. And now, in fact, right, if we perform this experiment not sending in a whole beam, right? Because you might think, well, maybe, when we combine the beams, they'll interact with each other. We do this experiment one electron at a time. You can theoretically even space them out years, right? One electron at a time. There's going to be no interference between, electrons that are nearby, right? Even if we do that, one electron at a time, and just send, no matter what we measure it as, we send it through the color box, right? Right? We don't look at the measurement of the electron. If we're looking at the measurement of the electron, we know it's hard, then send it through the color box, then, But if we measure it without looking, right, without knowing what the measurement is, we put it through a hardness box, then combine the beam. We don't look at the hardness measurements, right? We send the electrons one by one. No matter what this measurement is, we send it through the color box, right? All the electrons will come out white. And that's weird, right? Somehow just combining these beams will change it, even though we've already measured it, right? So it's not just the measurement, the act of putting it through the hardness box that messes this up. It's really knowing the measurement, knowing for sure that, if it enters this color box, it's definitely soft. That's what changes it. If we measure it, but then say, oh, I don't know if it's hard or soft, we already combined the beams, right? Then if we put it through the color box, it will act like we never even measured the hardness. So that is weird, right? And that is something that we're going to have to cope with in quantum mechanics. And throughout section 2, we are going to really be developing a way of understanding this extremely unsettling experiment. So I will see you in section 2.